So here's one that caused a little bit of difficulty. It's a more medium, easier one to start with. That's good. So for sure, this should be something that you should be able to sketch without a graphing calculator. This is really basic. So if this is difficult, you need to shore up your sketching and your basic functions. Get a crash course fast somehow. Y equals x squared. Y equals 0. What is y equals 0? X-axis. All the points where the y coordinate is 0. That's the x-axis. X equals 1 and x equals 2. What kind of lines are those? Someone knows. Vertical lines. So the region is y equals x squared, y equals 0, x equals 1, x equals 2. There's our region. And then we're going to rotate that about x equals 4. So let's talk about the two different ways we could do this, right? We could pick a vertical strip or a horizontal strip. And both would be valid. Both would get us the answer. Well, first of all, let's get the solid. So when you take that thing and rotate around x equals 4, when you're halfway around, where is this edge? This edge is at 6. And then where's this edge? 7. Okay? And so what will we have? We have something like this. Something like a Colosseum. Like that. These should be dotted. Okay. All right, so you get something that looks like that. We're trying to find the volume of that thing. And so let's talk about vertical slices first. If we did vertical slices, and we take our a typical vertical slice and rotate it about 4, what do we get? So imagine a vertical slice, rotate it about 4. What kind of element would we get? You should be thinking shell. That would be the shell. And that's the way we want to do it, right? Because we're practicing shells here. What if we did a horizontal slice? Okay, you're going to get washers. But what happens when you do horizontal? If you were to do this by horizontal slices, something happens. Notice that down here, the typical slice starts at 1 and ends at 2. But up here, the typical slice starts at the curve and ends at 2. So if you're going to do this by washers with horizontal slices, washers stacked up, you would need 2 integrals. You see that? You need 2 integrals. Because it changes. At this intersection point, your typical horizontal element would change, right? At that intersection point right there. So here's why. That's one reason why these shells are advantageous in this problem, because it just takes 1. And we're going to find out that the shell is quite convenient, easy. So our shell looks like this. So there's the typical shell, right? So the outermost shell is the shortest one with the biggest opening, right? And then the innermost shell, one that's enclosed by all the others, will be the tallest and have the smallest radius, the smallest opening, right? It'll be this tall and have the smallest radius. But they enclose each other, right? The thing about these shells is each one is wrapped around the next one, right? They're all enclose the ones inside of them. Okay, so the volume of a typical shell would be 2 pi r, right? This distance around times the height. And now it'll be delta x or delta y for this one? Delta x or delta y? Delta x. So that means we need the radius in terms of x and the height in terms of x. Okay? So what is the radius? So the radius, we ask, is it an x coordinate? So the radius, let's point it out first of all. So the radius is from your initial strip to the axis of rotation, or the center of the shell. So that right there is the radius. What I've marked there. Is that an x, a y, a change in x, or a change in y? Change in x, and we want to do final minus initial for change in x, or greater minus lesser. So what's the greater x value there? This is x2 here, and this is x1 here, where the strip is. So x2 is 4 for all the, right? x2 is 4, it's the center of rotation, it's radius. x1 is, it's just the x coordinate of this curve. So it's just x. So the reason that I'm having you start off by either writing x, y, x2 minus x1, or y2 minus y1 is because you don't always solve. You don't always change it into the other variable. So always start by writing one of those 4 things. Ask that question, is it an x, a y, a change in x, or a change in y? And then start by writing it that way, and then ask yourself, do I need to change it into the other variable, right? So this is just the x coordinate, this x1 here, is just the x coordinate of this curve. So we'll do 4 minus x. And then we say, do we need to change that in terms of y? No, because we're doing delta x. So it's just x, you see? And then when we integrate, so we're going to integrate all x values starting at 1 and ending at 2. So that's going to take care of what x values that is when we have the bounds of integration. So don't think that every time you substitute something into these formulas, you're going to change the variable, right? So always start by just simply the answer to your question. Is this distance an x, a y, a change in x, or change in y? And then, if you need to, write it in terms of the other variable. So what about h? Is it x, y, change in x, or change in y? So that's the height. That's this right here. Is that x, y, change in x, or change in y? That's just y. Do you see that? It's just y. So we're just going to write y. Now that one we need to change. That one we got to change into x because we have delta x. So what is the y value of the height of that slice in terms of x? That's just x squared, right? That's just x squared. So I think bypassing the step of literally writing down what it is, x, y, change in x, or change in y, makes then, then you get stuck here. You get stuck here. It's like, oh, is it y squared? Is it square root of y? No, it's truly an x1 or x final minus x initial, and we need it in terms of x, so it's just x. Doesn't make sense. So then we're going to integrate from the leastmost x of our slice to the greatest. So the volume is integral from 1 to 2, right? The first slice is here at 1. The shell that encloses all the others, and then to 2, the one that's enclosed by all the others. And so in this step, we're doing 2 things, right? We're summing up all the typical shells, and while thinking of them as really, really, really thin, right? Really thin. Questions on that? So I won't solve that one. That's really easy to solve. So, some of you had a little trouble on that one. Any questions? Okay, so let's do the next one, which was the one I got the most questions about. Okay, so first of all, we have to recognize that this curve is what kind of thing? Circle, radius. It's the radius. So, yeah, so x minus a. So let's review this equation of a circle. Should be, but you might have needed to reference that. So the center of the circle is a comma b, and the radius is 5. So we're going to have 0, 8, radius of 5. So we're going to be up here at, say, 0, 8. Radius of 5. So it's going to give us our circle like this. Okay? And then we're going to take, so, and it didn't, that's the only thing. It said the region enclosed by that curve. So that's the whole region. That's R. That's our whole region. And we're going to rotate that about the x-axis. The x-axis. So can you imagine what you'll get when you rotate that about the x-axis? So some people say it's a torus. Some people say, no, it's not. It's just a donut. Okay, so when you rotate that thing around, you get a torus up on its side, right? Which, of course, is just a donut. There's one right there, right? Okay, so we're going to get a donut up on its side, standing on its end, standing on its radial circular side. So we could do, let's talk about vertical slices. If we did vertical slices, what kind of elements would we have? Yeah, so vertical slices would result in what kind of elements? So if you take a vertical slice and you rotate that about the x-axis, washers, right? Washers. Horizontal slices, take that horizontal slice around the x-axis, that would be our shells. So we're practicing shells, so we're going to do shells. So here's a typical slice. And that's going to make our shell. Remember, what we'll call the height is always that distance from the distance from the top of the sleeve to the bottom of the sleeve. So in this case, the height is lying horizontally. So we're going to call this the height, always from circular side to circular side, that distance, the height. And then the radius will be from here to here. Does that make sense for that shell? And so all those shells, it'll start with a 0 height and the smallest hole, and then the height will increase as the radius increases to the maximum height at the center of the circle. And then as the sleeves continue to grow in radius, then the heights will shrink again until you get this 0 height again out at the very end. Okay, so we want our typical volume of our shell is going to be 2 pi r, 8. And are we going to have, for this one, we're going to have delta x or delta y? You should see it's delta y. That's, according to the strip here, is a little change in y. Okay, so the radius, is it x, y, change in x, or change in y? Radius, from here to here. You should see that is y coordinate. Y coordinate is distance from the x-axis. So our typical slice is just a y coordinate, okay? The height. X, Y, change in X or change in Y? Change in X. So we could write X2 minus X1. Now on this one, we could approach that height in a different way. We've seen it once before. What's another way to express that height? Because of the symmetry about the y-axis, that height is always 2x. So you could do x2 minus x1, or you could just say 2x. And so if you can recognize that 2x is a little bit easier, because then you only have one x value to find, right? x2 minus x1 means you have to identify two x values. But if you notice, this one has symmetry about the y-axis, so that height is 2 times x. So we'll go with that. So which one do we have to change? So 2 pi just stays, that stays y. And then we need 2x times 2, what is the x coordinate here? X coordinate is, well, it's the x coordinate of a point on the circle. So we're going to solve for our circle equation. It's going to be 25 minus y minus 8 squared, square root. So when we take the square root, you would have plus or minus, right? So the plus square root would be this coordinate out here, and the minus square root would be this coordinate over to the left. So if you did x2 minus x1, you'd have positive square root minus negative square root, which is the same as 2 times the square root. That's how it turns out to be the same. Right? So that the point on the right side of the circle is the positive square root. The point on the left side of the circle is the negative square root if you wanted to do x2 minus x1, but you get the same thing. Okay, so we got it all in terms of y. And so now the volume of our donut, or torus, is going to be the integral from, so we are in terms of y. So the first strip is at y equals what? Remember, this center was at 8. Our radius was 5. So with the smallest radius shell has a strip at y equals, you should see 3, 8 minus 5, and then the last strip will be way up here at the top, y equals 13. 8 minus 5, 8 plus 5. And then we're going to have 4 pi. So let's just take the 4 pi out. And then we're going to have y times the square root of 25 minus y minus 8 squared dy. So if you set that up correctly, and you were a little stumped on the integral, and you found another way to get that answer, I wouldn't give you that hard of a time, okay? But this is in the realm of all techniques we learned. So how are we going to do this with the techniques that we learned to do antiderivatives? It actually makes use of 3 different techniques to do this. Where would we start? No, don't FOIL. Don't FOIL. So notice what we have. 25 minus something squared, square root. That should remind you of something. What is tables, right? Tables. 25 minus something squared. Remember those a squared minus x squared was one in the table, was one of those forms in the table. But we got y minus 8 squared. So that would indicate we should change the variables. Change the variables. So if you do u equals y minus 8, well, we're going to have to take care of this y too. Then y equals what? U plus 8. Yeah, it looks like a W. You're right. Okay, and then dy equals. So it's a pretty easy switch. There's not much intricacy to the switch. And what do we got? 4 pi. 3 to 13. Not 3 to 13 anymore, right? So y becomes u plus 8. Square root of 25 minus u squared. du. Now what? So we got u plus 8. So the table won't have, a squared minus u squared times u plus 8. So we need one more step here. What are we going to do next? Okay, so really this has just become two integrals. Do you see this? U plus 8. So we have u times square root of 25 minus u squared. And 8 square root of 25 minus u squared. Are they both tables? Nope, they're not. This one is what? Yeah, undoing chain rule, right? Look, u is essentially the derivative of the inside there. So this one, we can just do undoing the chain rule. This is our table integral. So those were all things we learned. That was all stuff we learned. Change the variables with anticipation of using the table, but that actually turns it into two different integrals because it ends up being u plus 8. The u one gives us undoing the chain rule. This is straight table now. And then if you're going to change back, if you're going to use you could either just leave it in this variable u, and then what would, when y equals 3, u would be negative 5, and when y equals 13, u would be 5. So in terms of u, you could integrate, do from negative 5 to 5. Or you could change it back into y and do 3 to 13. Yes, sir? Yeah. How? Square root of 25 minus u squared. Yeah, so there's trigonometric substitution, but we never did that, and we just used the table instead. So that in terms of what we did, that would be a table integral. What's that? Yeah, sure. Yeah. So one of the techniques, most of the ones we had, the most common ones we had for table were, x squared plus a squared, x squared minus a squared minus x squared. Those are the ones we use the table the most for, especially if there was a square root on it, or like 3 to the 3 halves, or something like this, to some power, right? So these were the most common forms that we used the tables for. Sum of squares, difference of squares, often with square roots on them. That's what we use the table mostly for. Other questions? Okay, so there's two written. There's going to be another WebWorks set with shells, so more shells problems. But then there's a couple written problems I'm going to have you turn in, and I'll give you 5 minutes to look at those and talk about those. So let's do that. Just 5 minutes here. And that helps because that gives you what? The zeros, the roots, which are 0, 0, and 4, 0, right? And then, because of the minus x squared, does this open up or down? Opens down. When you have a negative coefficient of your x squared term, those parabolas open down. So then we know that vertex would have to be halfway between those two. So the vertex will be at x equals 2. And then y equals 3 would be up here. This. And then just one more hint. Notice this intersection point is the point 1, 3. That's helpful. Okay? So the first one, you're going to set it up using shells. Again, Washers is very inconvenient for that first one. That's why we want shells for that. Washers is pretty inconvenient. You can do it, but shells is a lot friendlier, okay, for that first one. The second one, set it up both ways. Set it up with vertical strips, whatever elements you get from vertical strips, whatever elements you get from horizontal strips, and then solve out the integrals, both of them, to make sure that you're going to get the same answer, right? Because it's the same volume, just should get the same volume value. Questions on these? So you're going to turn these in for written homework on Monday. Last chance for questions. Okay, so what we've done with the pancakes and the washers and can I get your attention off these problems now? With the washers and the pancakes and the shells, these are all what called solids of revolution, right? We always had some line that we took a region and rotated it around, right? So these are all what's called solids of revolution. So there's another way to generate solids. So can you sketch the region? Bounded by y equals 1/2 x squared plus 1 and y equals 7 minus x squared. Do that. That should be doable. Doesn't that just enough to get it doesn't have to be to scale, right? You don't have to be perfectly to scale with points, in the right place exactly. It's just enough to get going on these things. So what's the region bounded by those two? So rather than taking that region and rotating it about something, we're going to say that that's going to be the base. So the region, solid whose base is R, and is formed by square elements parallel axis. Okay, so R is going to be the base. Rather than rotating that about something, we're going to take square elements. So not shells, not pancakes, not washers, but square elements that are parallel to the y-axis. So can you imagine that? Can you imagine that? Is this what you got, first of all? So in that region there. So I'm gonna take strips that are parallel to the y-axis and then form squares out of those strips. standing up on this thing which will be the base of the solid. So can you imagine that? So if I turn this up like this. So now the y-axis is pointing back into the room. And so we're going to have a typical element will be a square whose side length is the distance between those curves parallel to the y-axis. So these will be all the squares, and we'll stack them all up against each other, and that'll form a solid. Do you see that? So what will that solid look like? Let's see if I can draw it. So the smallest, so we'll have, so let's just draw one square here. Like this to help us do that. Okay, and so then imagine the corner of all these squares up like this. You kind of see what that'll look like. Again, let me show you the different squares. So every cross section parallel to the y-axis is a square, and the base and the region you drew was the base of that solid. Yeah. What's so? It's straight. It's vertical, but it is curved because this is curved, right? So it's like a curved wall that's vertical. Does that make sense? The top or the back or the front? The sides would be vertical but curved. It's like a curved wall. It's like a curved vertical wall because it's defined by the curves, right? The sides are going up from this curved corner of the. Does that make sense? So they're not planes, but they're vertical, but they're curved. So just watch the side of the square closest to you. It's coming out towards you and now going back away from you. See that? Okay, so this is easy. If you understand what we've done so far, you can write the integral for this. This is easier than revolution. See if you can do it. Write the volume of the solid. Write the volume of the solid. And what are you going to imagine? What are you going to start with? What are you going to start with? If you're tracking with these volume problems, we should all be able to write this down. And that doesn't mean just write down the integral, okay? It means follow what we've learned. Follow what we've learned and you can do it. Follow what we learned and you can do it. I'll give you a hint. Here's your hint. That's really what we're doing. Okay. How many of you started out with the volume of a typical square? Not enough. Volume of a typical square is what? Side squared times change in x or y. It's going to be side squared times change in x. And then we ask ourselves, is the side A, x, a y, a change in x or a change in y? Change in y. Let's write it down. y2 minus y1 squared delta x. y2 is 7 minus x squared. y1 is 1/2 x squared plus 1. Same thing. It's just your element now is not a shell, it's not a pancake, it's just side squared times the thickness. It's just a square wafer element. And then we ask, is the side, is that, again, x, y, change in x, change in y. Change in y. So we got that, and then we're going to add them all up from what to what? Whatever this x is. That's -2. This is 2. So we're going to add them all up from -2 to 2. All those square wafers. Okay, so there's another shells part 2, and then there's some web work problems like this, and then the written homework. Okay.